You guys like to start with any kind of questions? Ready to start your exam? You got it. Questions? Up on web work and everything like that? Haven't checked yet. You had that big chemistry test last night and you're still not really all here? Okay, well, we're going to start section 8.1. In chapter 7, you learn all of your integration techniques. And there's a bit there in section 7.8 that I want to mention, but not necessarily cover. In section 7.8, there's something called hyperbolic functions. I never cover that section because I've lived all my life and never had to use a hyperbolic function, maybe more than once.
Oh, I actually had a question, actually.
Yes.
On so.
You guys see the board with the lines out? Sure does show it better on the Zoom.
It's the integral of natural log x squared plus 15x plus 56 and dx.
So when you see an natural log that's part of your integral, what is it that you think about ever? Look for u du, right? But if u is the logarithm, you need a du that has a 1 over that. So if it's not a u du, then it's got to be an integration by parts type u substitution, where u is the logarithm. So we're going to do this by parts. Where u is the entire natural logarithm. That means that the dv just has to be the 15x. Sorry, the x, dx, sorry. dv has to be the dx. And so we need the du and the v. The logarithm is 1 over u, so I got the x squared plus 15x plus 56 here. Then I have to take the derivative inside the parentheses, and I get 2x plus 15. And then over here, the integral gives me that v is equal to x. And so when we put our integration by parts scheme over here, u times v minus the integral of v du, I get x times the logarithm minus the integral of v times du. So I'm going to go ahead and multiply my v through the numerator here. And my numerator will look like 2x squared plus 15x. And then there's my denominator. And I'll let you stare at that for a minute. See if you know how to do that integral.
Break it up. Like, is it like, a over
We'll probably do that. One thing you gotta notice is that that fraction is not in reduced form. The 3 on top is not strictly smaller than the 3 on the bottom. So before you do partial fractions, you gotta put that fraction in reduced form by dividing. Do a little division on that. Need to divide. 3 on the top is not smaller than the bottom. So we're going to divide first. By He's gonna die first. That's why he's not die either. How about that? So we take the bottom into the top. X squared plus 15x plus 56 into 2x squared plus 15x. Looking at the x squared terms, we'll multiply by 2 and get 2x squared plus 30x plus front row 2 times 56. 2 times 6 is 12, about 112. Subtract that line from the line above it. The 2x squareds are gone. I'll have 15x minus 30x to give me a negative 15x, and then minus the 112. So this integral back here can be written as the whole part plus the remainder over the divisor. So let's put out over here. We'll first have the x times the natural log of x squared plus 15x plus 56. And then I've got minus. And I'm going to write that as 2 integrals. The integral of the whole part, 2, plus the integral of the remainder, that's the negative 15x minus 112, over the divisor, which was the x squared plus 15x plus 56. And I've lost room for my dx, so let's move that little integral sign out of the way. So I put the brackets because of this minus sign. I'm going to go ahead and put the minus sign back in. Go ahead and integrate that and write that as a minus 2x. Fix this minus sign. Keep those plus, but let's make both of those positive. And then as I do that, we'll see if we can factor that. We're looking for factors of 56 with the same sign that add to 15. Yeah, that's minus 2x. Take that minus sign inside the integral. Both of those positive. Let's see, what are factors of 56?
7 and 8.
7 and 8, 7 and 8, 56 it is, and 7 and 8 is 15. So the factor says x plus 7 and x plus 8. And now we're going to break that up with partial fractions. Yes, I'll do that right here, and then we'll come back and integrate that. Something over x plus 7 plus something over x plus 8. Partial fractions over here on the side. Cold hands, I think my little Scooby-Doo gloves. So here's the partial fractions. We got 15x plus 112 over x plus 7, x plus 8. Then I have a over x plus 7 plus b over x plus 8. And now we're going to multiply both sides by that denominator. So we have 15x plus 112 is a times x plus 8 plus b times x plus 7. I think we can get a and b by substituting in negative 7 and negative 8. So let's let x be negative 7. 7 times 15, let's see, that gives me 35. Carry the 3, negative 105 plus 112. Negative 7 plus 8 leaves me with 1a plus 0b. So a is 7. Now let's let x be negative 8. That gets rid of the a over there. 8 times 15 is a negative 120. And then a negative 8 times that gives me a minus b. So minus b is minus 8. That gives me b is positive 8. A goes on top of the x plus 7. So we put a 7 here and an 8 there. Well, just integrate. We've got our answer waiting for us. Final answer will be this x natural log of x squared plus 15x plus 56. Then minus the 2x from the dividing step. Then plus 7 times the natural log of x plus 7. And then plus 8 times the natural log of x plus 8. That's the arbitrary constants. So it's not lost. Let's put it in a nice little cloud. That had a lot in it. That was a nice looking problem. Yes, sir.
I solved this differently.
Oh, what'd you do?
I broke up the
logarithm. That's very smart. That's very smart. Let me show you what she's saying. Good gosh, I never think of the short way to do things. All right, so come back. Let me take the short way. We can get it done in about this much room. But you have to remember this formula. Does anybody remember what the integral of, say, the natural log of u is? Remember the formula? No? U, natural log of u minus u? So much. We could have done that, oh, so much shorter. Good gosh. Factor at this stage. And that's going to be our x plus 7, x plus 8. The logarithms have the property that the log of a product can be written as the sum of two logarithms. So we'll have the natural log of x plus 7 plus the natural log of x plus 8. We can have those as two different integrals using that. The derivative inside just gives me 1, so any substitution, for instance, would give me, if this is u, then that's du. Same deal here. So we just use this formula on each one of those. In this case, u is x plus 7. So we have x plus 7 times the natural log of x plus 7 minus the quantity x plus 7. Then we do it again for this one. And we get x plus 8 times the natural log of x plus 8 minus the quantity x plus 8. Like that one better? You remember this. But again, you can get that just by doing integration by parts. Here, use the natural log of x plus 7, d is dx. That comes out real quick if you do the integration by parts later. And never think of that. I've taught this class how many times, and I always do it the wrong way. Very clever, very, very clever. That's what I'm thinking, but I'm not quite sure. I thought of something I want to mention that showed up on your homework. I want to look at this integral. I don't know if it's the same one that's on your homework. Look at this improper integral from section 7.7. It has some details in there that are easy to overlook. I'm not gonna let you overlook it. The first thing is to notice you have an improper integral because the upper limit is infinite. So I do want you to take that extra step and write it as a proper integral using a limit. So I'm going to replace that limit, that upper value with m, and then I'm going to take the limit as n goes to infinity. Then we're going to think about how to do that integral in there. The degree on the exponent is the same as this degree on the stuff down here. So I can't do an ordinary UDU substitution. That means we're going to do this with integration by parts. So integration by parts, you take u to be the polynomial term and dv to be e to the minus x dx. And the derivative of x is 1, so du is just dx. What's the integral? E to the minus x. All right, minus e to the minus x. So now let's write that as the limit as n goes to infinity. And then here we put our uv minus the integral of v du. So uv gives me minus x e to the negative x minus the integral of v du. This is going to have to be evaluated from 0 to n once we get this integral done. So let me just hold off on that. Okay, so when I integrate this, I'm going to take this minus sign and put it with that one to get a plus. But then again, the integral v to the minus x is going to spit out itself and then the minus 1. So the end result is these three minus signs will give me one minus sign. So I have the limit as n goes to infinity of minus x e to the minus x minus e to the minus x. And now I have to evaluate that from 0 to n. Okay, I'm going to put an n in there for each x. There's the important part, so I'm not going to write it at the bottom of the board. I'm going to put it up here nice and big. We're going to have the limit as n goes to infinity. Putting an n in there gives me minus n e to the minus n minus e to the minus n. Now I'm going to put 0 in. This is going to give me 0 times e to the minus 0 is 0. But then I've got a minus e to the minus 0, which is a minus 1. This limit we can do right here. It's this last term. As n goes to infinity, this behaves like e to the minus infinity.
0.
That goes to 0. So this limit is 0. That goes to 0. But this doesn't. This one behaves like infinity times 0. Actually, minus infinity times 0, but infinity times 0 is not necessarily 0. Infinity times 0 is an indeterminate form. So this has an indeterminate form that involves some steps. If you remember from your glorious Calculus 1 days, when we were studying L'Hopital's rule, these types of things showed up, and our job was to write it either in the form of 0 over 0 or infinity over infinity. So typically, we took one of the terms and put it in the denominator and made the exponent negative. So I'm going to do that, but I'm going to take the term with the negative exponent and put it in the denominator to make the exponent positive. So with that particular thing, we're going to have a limit as n goes to infinity of minus n divided by e to the positive n. And that was 0, and that's going to be just plus 1 on the end of this. But now this has the right form to use L'Hopital's rule, because the numerator is infinite and the denominator is infinite. Whether it's plus or minus, that doesn't matter. But we do L'Hopital's rule, which says the limit of that expression can be found by taking the derivative of the top and dividing it by the derivative of the bottom. And then we look at the limit from that. The derivative of the top will give me a minus 1. The derivative of the bottom gives me e to the n. Now n is going to infinity. E to the infinity goes to infinity. And this behaves like 1 divided by infinity. What's the size of 1 divided by infinity?
0.
0. So that limit is 0 for that reason. So I get a 0 out of that, a plus 1 out of this. So I get that my integral converges to 1. What we do today is also going to involve limits. So I want you to remember L'Hopital's rule and what our indeterminate forms were. And so that'll be a good place to start right there. Okay. That's one of your write-up problems, I think, in your section 7 homework. Some version of that. Any questions?
So what were the indeterminate forms again? It was infinity times 0.
So the indeterminate forms for L'Hopital's rule are 0 over 0 or infinity over infinity. The ones that require some steps are infinity times 0, infinity minus infinity, and then we had some exponential forms that look like 1 to the infinity. I think it looked like infinity to the 0, maybe. Let me look them up. Make sure I get them all. Got 0 to the 0 is another one of them. So we're going to do some limits today with these in our section 8.1 problems. So I'll remind you of how we handle those limits again. Okay. Anything else? Okay, so here's a brief overview of the section that I'm not going to teach. I think you've seen some of these things. Hyperbolic trig functions exist. They are real. They come from ratios of exponential functions. And they're used primarily, or what I've seen them used in maybe fields of physics, electrical engineering, those types. Did any electrical students in here? You can see these again. So, I want to read 7a? Talks about the hyperbolic trig functions. And they come from ratios of exponential functions. The sum e to the x plus e to the negative x. When you average those two guys, you get a function. And that function is called the hyperbolic cosine. And it's written as COSH of x. And you say it as cosh of x. If I subtract in between, that's going to be the hyperbolic sine. SINH of x. And you pronounce that one sinh. We have the cosh and the sinh. What do you think the ratio of the sinh with the cosh is called? I call it hyperbolic tangent. So if I take this and divide it by that, the 2's will cancel, so we get this ratio of exponential functions. These things are used in modeling behavior of things that look like something called a catenary. Catenary. One of those little yellow birds? No. A catenary is a curve that has a form like that. Kind of looks like when you hang a wire and they get, little limbs. It looks like the natural curvature that you see in wires. I maybe overly pronounced it. This curve, the catenary is a curve with the equation having a general form of some number times e to the x over 2 plus e or over a, sorry, it could be any number there, e to the negative x over a all over 2. So it's some version of cinches and cosh. But they're functions that are related to something that's hyperbolic in shape. That's an A, just some random constant A. So our trig functions are related to circular behavior. Our hyperbolic trig functions are related to hyperbolic behavior. So there are things that are quite a bunch of hyperbolas pieced together. So we describe hyperbolic behavior. If you take the reciprocal of the hyperbolic cosine, you get the hyperbolic secant. That thing flipped upside down. The reciprocal of the hyperbolic sine is the hyperbolic cosecant, and the reciprocal of the hyperbolic tangent is the hyperbolic cotangent. They're functions of x that involve e's. So if you wanted to differentiate these, you just take the derivative of that. So let's do that. Let's take the derivative of the hyperbolic cosine. Derivative with respect to x of the hyperbolic cosine of x can be found by taking the derivative with respect to x of e to the x plus e to the negative x over 2. That 2 is a constant. I can pull it out as a factor of a half and then take the derivative of each term. So I take the derivative of e to the x here, and I get e to the x. Take the derivative here, the derivative upstairs gives me that. And so looky there, the derivative of the hyperbolic cosine is equal to the hyperbolic sine. hyperbolic sine, by taking the derivative of each of these e's. And the only thing that's going to change is you'll get a plus here. So the derivative of the hyperbolic sine is equal to the hyperbolic cosine. What do you think the derivative of the hyperbolic tangent is going to give you? What's the derivative of the tangent of x? Secant squared. The derivative of hyperbolic tangent is going to give you a hyperbolic secant squared. So they all look the same. The only difference is we don't get the minus signs. We can also integrate these things. You want to integrate this, you just integrate that. When you integrate e to the x, you get e to the x. When you integrate e to the negative x, you get negative e to the negative x. The 2 is a constant. You put it back in on the end, and that tells you that the integral of the hyperbolic cosine is the hyperbolic sine, and vice versa. So we can integrate them, differentiate them. We have versions of the Pythagorean theorem. Let's look at what the hyperbolic sine squared plus the hyperbolic cosine squared will give us. Does it give us 1? What sine squared plus cosine squared does? Let's find out, shall we? Let's compute hyperbolic sine squared plus hyperbolic cosine squared by taking their exponential versions, e to the x minus e to the negative x over 2 squared plus e to the x plus e to the negative x over 2 squared. The 2 squareds are easy. I'll just get a 4 on the bottom. To square the numerators, you got to FOIL it out. So let me put the 1/4 out front. When I square that, I get the first term squared. E to the x all squared is the same as e to the 2x. Then I'm going to get twice the product of the 2. Well, what do you get when you multiply e to the x with e to the negative x? E to the x times e to the negative x. When you multiply like bases, you add exponents. So you get 1. We're going to get that done twice with a minus sign. So we're going to get a -2 here. And then the last term will be plus that last variable. E to the minus x all squared gives you e to the -2x. Then let's square that one. I get the 1/4 for squaring the 2. I get the same 3 terms, but they're all going to be positive. We get e to the 2x plus 2 plus e to the negative 2x. So 1/4 e to the 2x plus 1/4 e to the 2x gives me 1/2 e to the 2x. 1/4 of -2 plus 1/4 of +2 gives me 0. And then 1/4 of e to the negative 2x plus 1/4 of e to the negative 2x gives me 1/2 of e to the negative 2x. So what is that sum? I don't know. That's e to the 2x plus 1 over e to the 2x times 1/2. I don't think that's going to give me a nice pretty 1. How come? You can write that as 1/2 e to the 4x plus 1 over e to the 2x. Geez, that didn't look like anything to me. I thought it was supposed to give me 1. Maybe it does. I just don't know how to get there. Oh, minus will give us 1. Minus gives us 1. That gives us nothing. minus here. With a minus here and a minus there. So, and so, and so, what do I get if that's a minus? I get, let's see, if that's a minus, I get a 1/2. I get a minus when I wrote it backwards. So you know the way, right? That one's gonna add out with that one, that one's gonna add out with that one, and I get 2/2. So here I get a -1. So cosine squared minus sine squared will give you +1. So the moral of the story is, other than my clumsy calculation, we have some versions of all of our Pythagorean identities. These functions also have graphs which over a certain interval are 1-to-1. Exponential functions are 1-to-1. So 1-to-1 functions have inverses. There are such things as an inverse hyperbolic sine function, an inverse hyperbolic cosine function. So their derivatives and their anti-derivatives, and they mimic pretty much the behavior of the e's because that's what they are. So found when I was a college student, I had to study this. I had a whole nother list of derivative formulas, anti-derivative formulas, trig identities, inverse hyperbolic trig functions, derivatives of those, integrals of those, and it was just a little memorizing game. And all you can do, the easiest way to remember is just go back to these two and try and integrate them. So why memorize more? Because it went in that head, right out there, and I've never used it again. But it's there, and when you see them in another class, you'll say, oh, that's what that is. So read that section, take a look at it. We're done learning our integration techniques, but there's still a whole boatload of things that you're not going to be able to integrate by parts or substitution or trig subs or partial fractions or some of the other clever manipulations. There's a whole world of integrals out there that don't have a closed form integral for, a formula for the integral. So we've developed techniques of integrating them, and one of them involves writing functions in terms of polynomials that have equivalent domains. We're working toward that. We're working toward making these polynomials that are equivalent to functions. But we have to know that those polynomials only behave like the functions on a small or in a subset of the number line and not necessarily over a global portion. In order to do that, I'm going to do some analysis with things called sequences and series. And that's what we do in chapter 8. Once you finish chapter 8, you have a little bit there to get you ready for calculus 3, where we talk about vectors. Your calculus 3 is going to start with calculus of several variables and then go into vector calculus. So everything we do now is building blocks for your Cal 3 success. For those of you who are taking Cal 3, just by showing up. I didn't mean that. Come anyway, just for social experience. Section 8.1. So your third exam starts from here. Sequence is some list of numbers. doesn't have to be numbers, but we're gonna work with numbers. We have some discernible patterns, for example, 1, 4, 9, 16, 25. That's an example of a sequence. 1, 4, 7, 10, 13. There's your sequence. 1, a half, fourth, an eighth. There's another one. 1, 1, 2, 3, 5, 8. There are 4 examples of some sequences that come to mind. You may have seen sequences before when you took maybe a version of a finite math class or a discrete math class. Where are my computer science majors? None? In computer science, you always want to develop some sort of formula to describe that pattern. So we're going to see if we can predict what the next term or two is in each of these patterns. Then we're going to redefine a sequence so that it has a more mathematical name or description to it. And we're going to look at general formulas for these. So what do you notice about the pattern in the first list there? If I were to ask you to guess the next 3 terms, if I just had a blank, comma, blank, comma, blank, would you know what goes in there? What would be? 13. You had a 25. I don't think so. 11.
36, 49, 64.
36, 49, 64. So there might be an easier way to look at this than just adding consecutive odd numbers. We notice about the numbers in that list. They're all perfect squares. We have 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, 8 squared. So if I take out using the k term, it would be k squared. Right? All right, what about the next one? Can you tell me what the next 3 terms are? So fast.
Each one has a difference.
Each one has a fixed difference of 3. Always adding 3 to get down the line. A type of sequence in which there's a common difference between 2 terms is called an arithmetic sequence. Seen those before? An arithmetic sequence. The next term is equal to the previous term or the current term plus a fixed number. Come back to that in a minute. What are we doing to generate the terms in the third example?
Divided by 2.
Each one's half the previous term, right? Half of 1 is a half. Half of a half is a 4. Half of a fourth is an 8. So the next one would be 1 over 16, 1 over 32, 1 over 64. The type of sequence where you take the previous number and multiply it by a fixed number to get the next one is called a geometric sequence. And multiply by a fixed number to get the next term. Then I see a pattern on the next example.
Fibonacci sequence.
That one is called a Fibonacci sequence. Let me see if I can spell that. sequence. Fibonacci sequence has a recursive pattern in that I get, say, this term by adding the two terms right in front of it. So I add the 2 plus 3 to get 5. I add 3 plus 5 to get 8. So the next term is 5 plus 8, which is going to give me a 13. Then I add 8 plus 13 to give me 21. And now I can't add anymore. Fibonacci studied plant life, and some patterns of petals or cell structures follow a Fibonacci sequence. Maybe you've seen the Fibonacci sequence with the little bunny story. If you had one female bunny or one male bunny, and then they can propagate after a certain period of time, and so they do, and then there's that many, and I don't remember how the story goes, because bunnies, they're like, I don't know, but that sounds a funny story with that. When you see Fibonacci sequence, how do you know about that?
In high school, we talked about recursive functions, and that was one of the prime examples for writing.
You said the magic word, functions. We're not going to call a sequence a list of numbers. A sequence with its mathematical definition is a function that maps the set of counting numbers to a real value. We're going to denote a sequence with subscripted letters of the alphabet. So I'm going to denote a sequence like this. If I get over here to the kth one, it'll be AK. And the one right before it would have a K minus 1 subscript, and the one right after it would have a K plus 1 subscript. So if I define these as function, the input is the place that the object appears in the list, and the output is the value that is in that slot. So a sequence is a function that maps our counting numbers to a real number. So I can look at it as a pairing between two sets. This set on my x-axis, or that would be my subscript, maybe it'll be a K or whatever. So that'll be my counters. And then this is going to be the value that appears in that list. So that'll be the AK. So for instance, A1 might be a particular value. Here's A2. A2 might be some other number. Then A3. And then maybe A4. And so you get a sequence of just a bunch of points in the XY plane. We're going to look at infinite sequences. And since they're functions, we're going to try to come up with either a general formula for the kth term or a recursive formula for all of the terms. Here's the general formula for this sequence, k squared. So I can rewrite that first sequence like this. So we're going to take our list of numbers and we're going to put them in these cute brackets. And then we put the formula right there. Use whatever subscript you want. I will often go between k's and n's. So this first sequence we can write as the list of k squares. For the second one, let's look at this recursively and see if we can go from recursive formula to a general formula. In this sequence, we said that we can write the next term by adding 3 to the previous term. So when we look at that one, rub all that other junk out. For this one, I would say that A1 is equal to 1. And then A2 is equal to 1 plus that 3. And then A3, which is this guy, the guy in the third slot, is 4 plus 3. But I got the 4 by taking 1 plus 3. So I can think of that as 1 plus 3 plus 3. And then the fourth term in that list is that 10, which is 7 plus 3. But that 7 was 1 plus 3 plus 3. So I can write that as 1 plus 3 plus 3 plus another 3. So to get here, to get to the 25, I have 3. Oops, wrong one, back up. To get to the 13, I have 1 plus 3 plus 3 plus 3 plus 3. I add 4 3s to get to the 5th term. I add 5 3s to get to the 6th term, and so on. So if I can write that in general, if I'm out at the kth term, I can start with the 1 and add how many 3s to that 1 to get to the kth term. To get to the second, I added 1. To get to the third, I added 2. To get to the fourth term, I added 3. So how many 3s do I add to get to the kth term? K minus 1. I'm adding K minus 1 3s. And so if I multiply that out with like terms, I'm going to have a 3K minus 3 plus 1. Here's a general formula that gets me that list. 3K minus 2, where K begins at 1. Let's try it out. If K is 1, I get 3 minus 2 is 1. If K is 2, I have 6 minus 2. There's the 4. Let's jump down here to the 6th term. If K is 6, I have 3 times 6 is 18, minus 2 is 16. So we can make a formula. It's going to give you the term. If you know the term number, you just feed it in, and that gets you the term. So I want to do it backwards now. I want to give you the general formula, and you tell me the first few terms. So this is called a general formula. For a term. So in these examples, I want you to write out the first few terms. The sequence with the given general formula. Write out the first few terms for the sequence with the given general formula. Let's start with example 1. General formula is just going to look like, I'll use n's this time, n squared minus n. N is a counting number. Write out the first few terms, you just replace n with 1. 1 squared minus 1. Can you do that in your head? How much is 1 squared minus 1? All right, next one, n is going to be 2. 2 squared minus 2. Now n is 3. 3 squared minus 3. And now n is 4. 4 squared minus 4. Let's do one more. 5 squared minus 5. There You know, the general formula works. Next one, let's look at sequence that has the pattern of n divided by n plus 1. All right, start calling them out. Start with n is 1. What's our first term? It's 2.
Thirds.
And it's 3. It looks like I always have my numerator to be one less than the denominator. So if I wanted to predict, say, a 50th term, might be something like 50 over 51. Right? I can jump in anywhere and find the number term just by plugging that number in for n. How about this one? General term is minus 1 raised to the n power. Let's go. First few terms. Minus 1 to the first power. Minus 1 squared. Minus 1 cubed.
1. Negative 1.
All right, so what you should notice about this first one is that these numbers get progressively larger and they're going to keep getting larger the further we get out. Right, if I'm out at the 100th term, I have the term that looks like 100 squared minus 100. That's a pretty big number. Here, my terms just bounce back and forth between 1 and negative 1. If the slot is in an even numbered slot, it's a 1. If it's in an odd numbered slot, it's negative 1. But this one, the numbers start to taper off. Look at the 100th term. It looks like 100 divided by 101. The 1,000,000th term looks like 1,000,000 divided by 1,000,001. Those ratios all are approaching a fixed number. These ratios are all converging to a limit. If I was way out here, if I kept making this list all the way around the room till I got to that corner of the board, my numbers start to get closer and closer and closer and closer to what number? Get closer and closer to 1. This is an example of a sequence that converges to 1. This sequence does not converge because the numbers get exponentially larger. This one does not converge because it oscillates back and forth to 1. So the sequence with a general formula like that will converge if that general term has a limit as n goes to infinity. We'll make the picture first and then we'll look at taking limits of those. Remember, a sequence looks like a bunch of dots going down for each integer value. So if this is the picture of a sequence, again, those are the subscripted A's, that's the counter. So if these are my integer values here, and then I'll break up my number line and go out for a bit. So my values might bounce around a little bit. But then if after I pass a certain big number, my values all begin to hover around a fixed number, say L, after we pass a certain big number, then we say that that sequence has a limit of L. So the sequence AK converges to a value L if the A K's approach L for K bigger than some large number N. Doesn't matter how much squiggling is going on here, but once you cross that threshold of a large number N, they all hang out at the same place, around that number L. So we say that AK goes to L if the limit as K goes to infinity of the general term is equal to L. If it doesn't have a limit, then the sequence diverges. If no such limit exists, we say the sequence diverges. And so we're taking limits to infinity, which we did way back in chapter 5 of your Cal 1 class. Were you present that week in class? Or were you like these people? You absent that week in class. Let's look at the one that we said approaches 1. I'm using the variable n. So let's look at taking the limits. Limits as n goes to infinity of that ratio n over n plus 1. So we can see that it goes to 1, but how do we compute that limit?
Or just like get rid of the one basically. Just have it as.
Say it again.
Just like get rid of the one basically, just have it as.
Pretty much, because when n is large, the 1 is not important, right? So this thing is behaving like the ratio of the n's, and they're both of the same degree. And we remember from calculus 1 that when we're taking limit to infinity and we have the same degree up top as on the bottom, then the limit is just the ratio of the coefficients. Remember that? And so that gives us 1. And so if we had something like, for instance, the limit as n goes to infinity, we get a 4th root of n up here, minus 3 times the cube root of n plus n up there and downstairs. I'll have 5 times the 4th root of n plus 2 times the cube root of n plus 7n. And I want to know what the limit of that is as n goes to infinity. Well, when n is large, the 4th root of n is not nearly as large as the cube root of n. And the cube root of n is not nearly as large as n itself. So when n is large, this is guiding the direction of the numerator, the last term. The same deal down here. For larger values of n, these numbers are smaller than that one. So this has all of the behavior of the function. They're both n to the first powers as the largest power of n. And so when I said you just look at the coefficients, then that has a limit of 1/7. What happens if the degree on the plan is bigger than the degree on the plan? Suppose I have n over n squared plus 1. That goes to 0 because it's a bottom heavy relationship. What if it was upside down, like this one? So I have an n squared minus n over even an n. That's going to go to infinity, so it has no limit. No finite limit, right? Anything that oscillates back and forth has no limit. You would say the limit as n goes to infinity of minus 1 to the n does not exist because this oscillates. negative one, right? The picture of this one looks like this. First one was a negative one, next one was a 1, then a negative 1, then a 1, then a negative 1, then a 1. So there's no single value of L that these points all gravitate towards. Now, if it's not that easy to see, if we're not talking about degrees and things like that, we use the fact that to get these general patterns, we use the fact that 1 over n to a power goes to 0 as n goes to infinity. And so I can show you that this thing has a limit of 1/7 by getting rid of these terms here. The way we did this in calculus 1 is we looked at the highest power of n, and then we divided each term by the highest power of n. That was equivalent to multiplying by 1. Right? Let's go back to 4 root of n minus 3 times the cube root of n plus n. Let's divide all of those by the highest power that we see. And then same on the bottom. Divide each of those by n. So what I've done is I multiplied the top by 1 over n and the bottom by 1 over n. And 1 over n divided by 1 over n, as long as n is away from 0, is like 1. If we're way away from 0, losing it as n goes to infinity. Then these things can be written in reduced form that look like the n to a power underneath the constant. I can rewrite that one as 1 over n to the 3/4, subtracting exponents. The middle one I can write as 3 over n to the 2/3, and the last one can look like a 1. Same deal here, I'll have a 5 over n to the 3/4 plus 2 over n to the 2/3 plus 7. And now we're going to take that rearranged form and take the limit as n goes to infinity. And what this is telling me is terms that have the n underneath the constant are all going to peter out when n gets large. They all go to 0. And that's where we came up with the general pattern. We can just look at the highest power on the n. Remember that? That's the way you guys did it in your calculus 1 class? So one way we're going to evaluate these limits is just look at the ratio of the highest powers. But then the other ways is that we've got that handy dandy L'Hopital's rule. We can always take the derivative of the top and divide it by the derivative of the bottom to see what the limit goes to. So one of the things that we're going to do, the question will be, does the sequence converge? And so when you hear that statement, you say, does the general term have a limit as n goes to infinity? So if it converges to what? To what does it converge? My first one. E to the minus 1, e to the minus 2, e to the minus 3, e to the minus 4. That's the terms in this sequence. What's your intuition? Goes to 0. Limit as n goes to infinity of e to the minus n. Looks like the limit as n goes to infinity of 1 over e to the positive n. E describes exponential growth, so the bottom gets bigger and bigger and bigger and bigger. So that one does converge. This one converges to 0. List of numbers, arctangent of 1, arctangent of 2, arctangent of 3, arctangent of 4. Those numbers converge. If so, to what?
Pi over 2.
Pi over 2. This has that asymptote there, so this one converges to pi over 2. This one we're not going to have time to do. This one takes some time. This one will leave you hanging for a whole week. Because this limit here has an indeterminate form. It behaves like, well, I'm adding two very large numbers together. After I square one of them, then I take the square root. Those numbers are so large, taking the square root keeps it large. Then I'm subtracting another large number. So it's behaving like infinity minus infinity, which is an indeterminate form. So I'm going to have to remind you how to handle indeterminate forms that look like that. We did an example of the indeterminate form of 0 times infinity when we computed that definite integral at the beginning of class. We're going to do some more like that. We're going to look at how to handle the exponential forms that were indeterminate. So we'll go back and look at stuff like that. I guess the week after we come back, we're going to review for your test on Monday, have your test on Wednesday, so we'll come back to this on Friday in 2 weeks. Good? All right. You guys have an enjoyable break. I've got all of your web works open for chapter 7. So if you've got some free time, go back and max out your scores on those. For studying over the break and run into trouble, send me an email. Pretend like I know you and answer you. All right, you guys are going to you guys have any questions? Good.